Alright, Pre-Calc BC, on to day 11. Today we're going to talk more about velocity and other rates of change, and we're also going to explore what's happening in our velocity graphs some more. I also I'm going to post this picture here, which is going to be part of our last problem of notes today. And instead of writing this all down in the video, you can kind of do that on your own time. I've already written it down, and I'm just going to kind of walk you through like what I see, and then you can actually write down yourself what you find most important. Okay, but we'll get to that at the end. So first thing, we're going to write the circumference of a circle as a function of the area. So this is something we've done a couple times this year, where we write one equation as a function of another. So you do need to know your formulas for both of these. Circumference is 2 pi r, and area is pi r squared. And I don't know if I ever told you the rhyme that I created when I was in high school, so I would remember these formulas. If not, I'm going to share them with you now. It's, twinkle, twinkle, little star, circumference equals 2 pi r, fuzzy wuzzy was a bear, area equals pi r squared. I know, that's really beautiful. We're very happy to hear this. So I'm writing the circumference. So I want this to be a c equals, but I want it to be as a function of area. Right now it's as a function of radius. So I need to go ahead and solve for radius in my equation over here. And square root that. And we're going to say my radius has to be positive, so I'm not going to put my plus or minus. I'm doing that on purpose. So circumference is 2 pi square root of area over pi. So that's circumference as a function of area. Beautiful, just beautiful equation. You're totally going to use that all the time. So now we're going to find the rate of change of the circumference with respect to area. So that's going to be dc dA. And before I do that, let's just kind of clean this up a little bit. So I'm going to rewrite this as 2 pi times root a over root pi, and oh, that's an h. And these guys here are my constants, so I'm just going to kind of basically like rearrange this. And then a would be to the 1/2 power, right? Because it's a square root. So now I'll go ahead and I will find my derivative by doing power rule. So I'll bring my 1/2 forward. So 1/2 times 2 pi over root pi, a to the negative 1/2. Okay, and my 1/2 and my 2 here are going to cancel. And then if you want to just rewrite this, it would be pi over root pi, and then the a is going to go down as well and also be in the square root. So it would be like that. And that's c prime. Okay, and then we're just going to evaluate the rate of change at a equals 4 pi and a equals 16 pi. Oh, and I guess technically speaking this part b was still part a. So now we're on part b. So we're finding c prime of 4 pi and c prime of 16 pi. So we'll just plug our 4 pi and our 16 pi in for area in this equation. So that would be pi over the square root of 4 pi squared, which is going to be pi over 2 pi, which is just 1/2. And this would be, we weren't given units, it would be inches of circumference over inches squared of area. And then 16 pi, we'll just do the same thing, we'll plug that in. So pi over 4 pi, so that would be 1/4. And then with the same units, inches of circumference over inches squared of area. All right, great. Let's take a look at the next one. Next, we're going to, given the following coordinates, plot a graph of s versus t. We are not going to do that. Not interested. Instead, we're going to estimate the velocity at t equals 1, t equals 2.5, and t equals 3.5 seconds. So we're just going to do 2 of these. I don't think we need to do t equals 3.5. It's going to be the same method for each of these. So when you're estimating, we're kind of going to use the idea of the symmetric difference quotient that we talked about a few days ago. We're going to use the 2 points around the one that we actually care about. So at t equals 1 seconds, we're just going to find the slope using the 2 points on either side of it. Okay, so the velocity at 1 second, we're just going to do slope. So we would say -10 minus a -4 over 1.5 minus 0.5. This is your x and this is your y. So that's going to be a -6 over 1, which is just -6 feet per second. Okay, let's try one more. 2.5 seconds, that's right here. We'll just use the points on either side of it. And so again, this is going to estimate the velocity at 2.5 seconds. So we'll say this is 3.5 minus a -8.5. Again, change in y over change in x, and 3 minus 2. So that should be a 12 over 1, which is 12 feet per second. And because this is velocity, we can also say what's happening. Like if this is representing a particle or someone moving, they would be moving to the left at 1 second or down because we have a negative velocity, and they'd be moving to the right or up at 2.5 seconds because we have a positive velocity. Okay, and then if you want to do 3.5 seconds, you would just use the 3 and the 4. But I think you can do that on your own. Let's move on to something a little more exciting. Speeding up versus slowing down. This is like a super controversial topic. I want you to look at these given velocities and accelerations, and I want you to think about which of those objects are speeding up and which represent an object slowing down. Okay, and there are 2 of each. So I want you to pause the video. I want you to think for a second, which is talking about speeding up, slowing down. And when you're ready, when you have an answer, come back to the video. All right, so here's your answer. An object is speeding up when velocity and acceleration are working together and have the same sign. Okay, when is an object slowing down? An object is slowing down when velocity and acceleration are working against each other and have opposite signs. All right, so I was hoping to bring up my webcam so that I could have a visual, but apparently I can't do that once I start. So I'll just try to describe this in words. I want you to picture throwing a ball up in the air. If you throw a ball up into the air, it's going to have a positive velocity, like this situation right here. However, something that's always, a force that's always acting on this ball as it's in the air is gravity, as you know. And gravity is something that will always pull us down. So gravity is representing our acceleration force, and it's a negative. So think about, if the ball is going up, we've thrown it up, but this gravity force is pulling it down, what is that really doing? Well, it's working against the force that we are throwing the ball into the air, and in essence, it is slowing the ball down. So when we have an opposite signs for our velocity and acceleration, they're working against each other. When they're working against each other, they're going to be slowing the object down. Okay, this negative acceleration means that it is accelerating in the negative direction, so downward or to the left, like gravity. Okay, that's also happening here. In this situation, an object is going to the left or down because it has a negative velocity, but the acceleration is pulling it to the right. Well, if the acceleration is going in the opposite direction as velocity, again, we're going to be slowing down. However, if you have velocity and acceleration going in the same direction, they're working together, and that's going to be speeding up. Okay, so it's actually really easy to tell whether you're speeding up or slowing down. If the signs of your velocity and acceleration are the same, you're speeding up. If they're not the same, you're slowing down. That's it. All right, so this brings us to our last problem. It is going to take us a little bit, and then we're going to look at that other document that I showed you that I'm going to post on Canvas that I mentioned at the beginning. So Melissa is back. She survived crashing her rocket last year, and she is out flying again. Good for Melissa. She fires her retro rockets, causing the ship to slow down, stop, rise up again, and then come back down. Her displacement from the surface of the moon is this. All right, so this is position. Write equations for velocity and acceleration of the spaceship. All right, let's do that. Velocity, as we know, is position, the derivative of position. So y prime, which is equal to velocity, and we'll just go ahead and do power rule here. So bring my 3 forward, negative 0.03 t squared plus 2t minus 20. There's my velocity. And then the derivative of velocity is my acceleration. I'll just take the derivative of this again using power rule. Bring my 2 forward, multiply negative 0.06t plus 2. Okay, there are my equations. Find the acceleration at time t equals 15 seconds. At that time, is the spaceship speeding up or slowing down? In order to tell which it is, you also need to find velocity. Okay, so even though it doesn't mention velocity, speeding up or slowing down, we are going to have to look at both. So a of 15, we'll plug that into our acceleration formula. And negative 0.06 times 15 plus 2. So that's 1.1. And are we in meters? Did I tell you where you are? Kilometers? Okay, kilometers per second squared. So that's acceleration. Now I'm going to check velocity. Velocity at that same time. So make sure you use the right formula. Okay, and I'm just going to tell you what you get when you plug it in. When you plug it in, I have that you get a 3.25 kilometers per second squared. Okay, so the actual value does not matter. Like, I don't care that it's 1.1 or 3.25. What I care about is that they are both positive. Since they are both positive, we are speeding up. If they were both negative, we would still be speeding up. Okay, it's just telling us what direction we're going in. So both positive, that means that the ship itself is going upwards right now, positive velocity, and it's also accelerating upwards. That's why it's speeding up. Okay, C, find the values of t at which the spaceship is stopped. All right, so if the spaceship is stopped, that means that velocity has to be equal to 0. Okay, so one way you could do that is just plug a 0 in for v. And you could try to factor this, but I don't think that's going to factor. So instead I'm going to graph it. You could use quad formula. I know some of you love quad formula so much. Okay, I gotta change my window. Okay, those are... Let's go to the right. Let's see if that helps. There we go. Okay, so there's my parabola. I'm not gonna draw a picture of it, but we are looking at when velocity is 0. So again, this is the velocity curve. Velocity is 0 when you're hitting the x-axis. So I'm just going to go ahead and find those 2 points. 12.251 seconds. Okay, I'm going to say graph it. 12.251 seconds. And 20 hours later. 54.415 seconds. Okay, so again, that was the velocity graph, and we wanted it to be stopped, so velocity equals 0. So that's where the velocity graph hit the x-axis. Just do a very brief sketch. So these guys. Okay. When does the spaceship touch the surface of the moon? What is the velocity at that time? Explain what you think will happen to the spaceship at that time. So we're talking about the spaceship touching the surface of the moon. Touching the surface of the moon, that would be displacement. So we're again going to set our equation equal to 0, but we are going to need to set our position 1 equal to 0. T squared minus 20t plus 200. Okay, so depending on the question, you're going to have to graph different things, or different functions, I should say. Okay, I think I typed that in right. Let's do a zoom 6. Okay, let's look at our table. Alright, so our values are super high up, so I need to change my window big time. I'm just going to go with like 300. Let's see what that does. Okay, I'm going to move farther to the right also. It is a cubic, so let's try going over a little more and up a little more and seeing if we can get the whole picture. Okay, I'm going to go up just a little more. Alright, there you go. There's that cubic that we're looking at. So, alright, when does the spaceship touch the surface of the moon? That would be right here. Okay, surface of the moon, because I'm dealing with position. So we got like, woo, like that. So this is when position is 0. So let's go ahead and find it. .531. So that's time. So that's when we're going to hit the moon, or touch the surface of the moon. And now we're asking for velocity at that time. So t is 77.531. We're going to go ahead and plug that into velocity. And I'm going to actually use the x value to get a very exact answer. So negative 0.03x squared plus 2x minus 20. And we get a negative 45.270. Let me write this down and then we'll talk about what that means. So I just plugged my 77.531 into my velocity equation. And I got out a negative 45.270 kilometers per second. So that's how fast Melissa is going when her rocket touches down on the moon. So I would say that's probably not good. I would say that she probably crashed, but I'm sure she's just fine. Oh, I put a smiley face. I didn't mean to do that. Crash. Very sad. Okay. I'm sure she's fine though. You don't need to worry about her. It's all good. Okay, so now if you flip, this is the last thing we're going to do. Using the graphs below, describe Melissa's space journey. Okay, so again, I'm not going to write out a whole paragraph here. We are going to look at this sheet here, which has everything you need to know, and I'm just going to run through what you should notice. Okay, so here is position, velocity, acceleration. I'm going to be honest, I really don't worry about the acceleration graph. I worry about the top two. Okay, everything that I need from acceleration, I can get from my velocity graph. So S of t, my position. First, I'm going to look at slope. Has a negative slope from 0 to 12.251 seconds. Notice that's also why we're in the negatives for velocity. Remember, velocity is the derivative of position. So what this means is from 0 to 12.251 seconds, Melissa is going downwards. She's also starting up at 200 kilometers because that's the starting point on her position graph, or the y-intercept. Okay. At 12.251 seconds, all of a sudden your slope changes to a positive. That means we're now changing directions. Since her velocity is now positive slope, she's moving up. So that 12.251 seconds, that's a change in direction. That change in direction happens again at 54.415 seconds because that's when she starts going down again. Okay, so negative velocity moving down. You can see all of that matching on your velocity graph. Before 12.251 seconds, we're in the negatives. Negative velocity means she's moving down. Between 12.251 and the 54 seconds, velocity is in the positives. Okay, that means she's going up. All right, she's going up because this whole thing is in the positives. It's representing this part of the curve right here in position. And then after 54 seconds, and I'm just chopping off the decimal when I talk about this just to make my life easier, she's going down again. Okay, so these magenta colors, they match, the yellows match, and the magentas match. Okay, the change in direction is again happening at 12.251 seconds and 54.415 seconds. Notice those are the maxes and the mins on the position curve, which are represented in the x-intercepts of the velocity curve. That's because at your max and min, your slope is 0 for your tangent line. So your y-coordinate, or your y-coordinate is 0, meaning you're dealing with your x-intercepts there. Okay, so we just talked about most of this. There's some more things I want to talk about though. 77.531 seconds, that was what we just talked about. That's where our position curve actually hits the x-axis, which is representing the moon's surface. That's when she crashes on the moon and is completely fine. All right, so that's what you need to know from the position curve. Let's look more at the velocity curve. So the velocity curve is where you want to look when you're figuring out if you're speeding up or slowing down. Okay, so for example, this purple part right here, magenta, fuchsia, whatever color you want to call it, the velocity is in the negatives, but you have a positive slope, right? It's going uphill. So that's negative velocity, positive acceleration. Those signs are opposite. That means we're slowing down, or we're approaching stopped. That should kind of make sense, right? Because look, this whole curve is talking about velocity, so you're getting closer to 0. If you're getting closer to 0, you're slowing down. Okay, so now, this yellow part right here that I've circled, you have a positive velocity, right? You're in the positives, and your slope is still positive. So acceleration is positive. Both of these are positives. That means we're speeding up, which again should make sense because we're moving away from 0. 0 means stopped, right? So we're moving away from 0. We're speeding up. Okay. Now, 33.33 seconds right here. We are still moving upwards because our velocity is still in the positives. But this is when we start slowing down. We start slowing down because now we have a negative slope, which means acceleration is negative. We are approaching 0 again, so we are slowing down. And then at this 54 seconds, now we're actually going downward because our velocity is negative. our slope is negative as well, so we have a negative acceleration. Here's where we start speeding up again. Okay, we're speeding up because we're both moving downwards and our acceleration is pulling us downwards as well. And we can see that because we have a negative slope. This AFT graph, I don't really do a whole lot with this other than up until 33 seconds, we're accelerating in the positive direction. And after 33 seconds, we're accelerating in the negative direction. The 33.33, which we can also see represented in the max here, that's just our max velocity, or excuse me, that's the time at which we have our max velocity. The actual maximum velocity would be the 13.33. So all of these x coordinates are referring to time, and then the y coordinates are referring to whatever graph you're on. So here the y is talking about your position. In this graph, the y is referring to your velocity. And in this graph, your y is referring to your acceleration. Okay, so hopefully that was helpful. I'm again going to post this on Canvas and you can print it off. And yeah, this would just be the information you should be able to take from a position and velocity and acceleration graph.